So I'm going to start recording. We are now in week 6. We're over a third of the way done with the semester. That's crazy talk. I feel like we've known each other forever. It's just like, oh my God. But we are now in lecture number 11, I believe. And we're going to start by going over the quiz. So please take out your quiz. So you have what I'm talking about. You can see it in front of you. I'm going to spotlight myself. People did well. Other people didn't do well. And most people did not get the last question. So I am opening up the... Adrian, you sent it to me again. I don't know why. I do have your quiz. I don't think I said you were the one who... I don't think I said you didn't. I didn't have yours.
Okay, I was just making sure.
So I'm not sure. Yeah, okay. So let me load up the question. So this is Math 211, Monday, Wednesday, under Files, and this was Quiz 2 PDF. Okay. So the question says as follows. Nikki has a train set with 3 different engines. So let's write that down. 3 engines. 3 engines. It has 8 different passenger cars. So we'll say 8 passenger, shorthand for passenger cars, and 2 different cabooses. What a great word, caboose is. So it has 3 engines, 8 passenger cars, and 2 cabooses. Namira, thank you. Because it's possible I couldn't find it. And in fact, yes, I have you written down that I'm missing your first quiz, so thank you. Anyway, Nikki always makes trains by putting 1 engine first, 1 passenger car second, and 1 caboose third. So Nikki is creating a chain of 3 cars, an engine, a passenger car, a caboose. So this is a chain of sequential decisions. The first decision Nikki has to make is to which engine he's going to use. How many choices does Nikki have for the engine?
3.
3, right? There are 3 engines. So choice number 1, 3 options. How many choices does Nikki have for the second, which is the number of passenger cars?
8.
8. So second option, 8. How many choices does Nikki have for the third, which is the number of cabooses?
2.
2. So by the fundamental principle of counting, the answer to the question is 3 times 8 times 2, which is 48 possible trains. That was the answer to part A. Part B. Nikki's sister grabs 4 of the passenger cars. Now, how many passenger cars are there for her to pick?
8.
8. So she's grabbing 4 of those 8, and she's running away with those 4. Does it matter the order that she grabbed them in?
No.
No. So this is what? A permutation or a combination?
A combination.
Combination. So we're looking for how many ways 4 can be chosen from 8 when the order does not matter. So if I was writing down my information, I would write down n equals 8. That's a number that we're picking from. R equals 4. That's how many we're picking, and that we're dealing with a combination.
Mm-hmm.
Once I have that information, I go to my formula, which is what? N factorial over?
N minus R factorial, R factorial.
Excellent. N factorial over N minus R factorial, which becomes 8 factorial over 4 factorial, 4 factorial. Correct?
Mm-hmm.
Yep. N is 8, R is 4. And then you do the math, and I think you get 70. So there were 70 possible choices that Nikki's horrible sister, who's doing nothing but ruining his fun, can make. Now, question C, very few people got right, but some did. I was very pleased to see. Nikki decides to make the train by putting 1 engine first, then 2 passenger cars, and then 1 caboose. So like the first situation, it's a sequential series of events, but this time there's 4 choices. Choice 1, how many engines can Nikki choose from?
3.
3. And by the way, of all the people who got it right, no one continued it from part B saying, oh, 4 passenger cars were gone. So we're assuming that that never happened. It's like its own standalone question. Now, the second choice Nikki's making is which passenger car to put here. How many choices does Nikki have for the passenger car to put here?
8.
8. Once Nikki has put that passenger car there, how many choices does Nikki have for the next passenger car?
7.
7.
7.
And then finally, Nikki's going to put a caboose. And how many choices does Nikki have for the caboose?
2.
2. So by the fundamental theorem of counting, the answer would be 3 times 8 times 7 times 2, which I believe was 336.
Okay.
Did that make
Wait.
sense?
I'm sorry, where did you get the 7?
Once one passenger car has been chosen to be in the first position, how many are left for the second position?
Oh, okay. Yeah, I got that wrong.
The
I
car that was
wasn't sure.
chosen can't go again, right?
Yeah, that makes sense.
Yes, Monica, if you don't mind, because somehow I missed it, and I apologize. But if you would not mind sending it again.
Okay. It's just I saw it right now on Canvas, so I don't know if you can find it, but I'll send it again.
Yeah, because I delete them after I grade them. So it must be that I graded it or accidentally deleted without grading it, and I apologize. But yeah, if you don't mind sending it again, that'll just be wonderful. That'll fix everything. So does that make sense for that question?
Wait, hold that up one more time, Professor.
Sure, or Solaire can show hers, but okay, that's fine.
3 times 8 times 7 times 2. Thank you.
Right? And notice how I kind of even write out slots for each choice.
Yeah.
And then I write down how many options there are for each one. The key, yeah, Nancy, that'll get it to me. Nancy, I have yours. I didn't say your name. I got yours. Oh, you're just telling her so that she knows it gets to me. No, Canvas gets to me as well. I just, for whatever reason, I must have missed it, and I apologize. Yeah, that email is the best in terms of grading, just the format, the way it comes in. It's the easiest for me to grade. So if you're going to send it to an email, do that one. But otherwise, I'll check them all. It's just I have to search around, and sometimes it's not as easy. But I will eventually get to it. Okay, so that takes care of the going over the quiz. Then people asked about the quiz today. I will post it after class. You will have 48 hours to do it. It'll be on chapter 4. The solutions to chapter 4 are up. You can peruse them, so you don't have to do the quiz today. You can go over the homework, take a day, take tomorrow, and do the quiz, let's say, on Thursday before class. That's up to you, or Wednesday before class. That's up to you. We're also about ready for the first test.
Oh.
Yeah, I know. Because chapter 6, which we're going today, is the last chapter for the first test. Let's see if we finish it today. If we do, the goal is for you to take the test over the weekend coming up, a week, like in 5, 6, 7 days, that type of thing. Of course, if we don't finish 6 today and we don't finish it till Wednesday, then I have to give you a little more time. So let's jump into 6. Please load it up. I posted it, so it should be there. I am going to share my screen. So I will try to annotate here. And chapter 6 is on the multiplication rule. So you're all with me here?
Mm-hmm.
Okay, so last section we talked about princesses and crowns and non-princesses and non-crowns and so on, right? So let's consider the following two-way frequency table. 2 ways, again, because you have 1 way here and 1 way here. We have a total of 100 girls. 60 of them have crowns. 40 of them don't. 10 of them are princesses. 90 of them are not. And the particular values in each section are 6, 54, 4, and 36. Now you'll notice, of the 10 princesses, what percent of those 10 princesses wear crowns?
60%.
60%, 6 over 10, right? So we're making a new table here where rather than putting in the actual numbers, we're putting in the percents. But we're not going to put in 60% because this table is not about of the princesses, although we'll get to that later. This table is out of the 100 total girls that we have. What percent of the total 100 girls are princesses that wear crowns? And the answer is, well, 6 out of 100, correct?
Mm-hmm.
And 6 out of 100 is actually 6%, 0.06, right? So we put a 0.06 in our table here. Of the 100 total girls, how many are regular girls who wear crowns?
Oh, wait, other way. 54.
So what percent? So 54% or 0.54, right?
Yeah.
For a total of 60% between them. Of the 100 girls, how many of them are princesses that do not wear crowns?
4%.
So that'll be 4%. And we see that that gives us a total of 10% here. And what percent goes here? 36. Someone's saying something. How do I scroll? Hold on. Oh, no problem. Okay. So back, oh, crapalola. So I lost it all. So this was 54%. This was what, 36%? Yes, sir. This was 4% for a total of 10% for a total of 90%, right? We can fill these numbers 40% and 60%. So this is a table here which cares more about percentages than it does about actual numbers. And sometimes percent is more important than actual numbers. And why can I not scroll? Okay, I know what I have to do. I have to stop sharing for a second. I have to download this and not do it on Zoom or whatever this is. Okay, there we go. So far so good?
Mm-hmm.
Okay, so let's now go to the next one. The question is, suppose that you only had the marginal proportions. You only had these numbers. And you also knew the very important fact that the variables were independent. The question is, from those two pieces of information alone, can I fill out the table? And the answer is yes, actually you can. If I didn't know they were independent, then any numbers that add up to 0.6 and 0.4 and 0.9 and 0.10 will be fine. But because they're independent, I get something for free. And what I get for free is that, well, let's see if anyone can think about it. Can anyone look back at the previous slide, look at the number that goes here, and see if you can figure out a method by which we can get that number from only these numbers?
Can you divide?
I was multiplying 0.10 times 6.
0.6, you mean, right?
Yeah, 0.6.
Yeah, so if I want this one, I can look at the bottom total and the side total and multiply them. What is 0.1 times 0.6? It's 0.06.
Why is that possible?
That's a great question. You're asking why it works?
Yeah, basically, like, why can we do that? I don't get the reasoning behind it.
We have a formula from before.
Mm-hmm.
Well, actually, do we have that formula?
I know that you said something last class about being independent and dependent.
I have to be honest with you. I can prove it, but I think that the proof would be too complicated. I think it would take too long. It's a wonderful question, and it's a great question, because why trust anything without proof?
Mm-hmm.
I guess when we can, I think we have this from before. Let's try this one. Don't we have the formula that if two events are independent, then the probability of both of them occurring is just the product of their individual probabilities. Have we seen that formula?
Can you repeat?
Well, I wrote it.
Oh,
The probability of A and B, if independent, if independent, then the probability of A and B is the product of the probability of A and B. If we haven't done that, don't worry about it. Maybe as
Yeah,
we later in the
I'm sorry to confuse anyone or.
No, it's a great question because you should understand why. This
But,
is the reason. This is the reason why. Because if A is crown and B is princess, then the probability of A and B, of a princess, of a crown with a princess, is the probability of A, the probability of a crown, which is 60%, times the probability of B, which is princess, which is 10%.
Okay.
So if this formula is true,
It makes sense.
okay, but understanding why this formula is true, I don't think we justified that.
Yeah, I don't think we've touched base on that.
I don't think so. Maybe we'll do it later in the section, and if we do, then
But,
we'll see why it's true.
So basically, to get that top number, the 0.06, we multiply 0.10, the total of the crown and no crown, and the total of
That's right.
the crown.
That's right.
Okay.
And if I want this number, yes, got it. Sorry, that bug's been killing me all day long. Finally crawled on my. I feel great right now. Okay, so if I want this one here, I go to this number down beneath it, 0.9
Right.
times 0.6, and I get 0.54, which, as you see in the previous slide, is correct for that one. And for this one here, I do 0.9 times 0.4, which is 0.36.
Oh, okay.
And if I want this one here, 0.1 times 0.4, I get 0.04. So you see that these numbers match up.
Okay.
This is only if they're independent. If they're not independent, you can't do anything.
Okay.
Okay, but if they're independent, it allows you to calculate the values. Okay?
Can you explain one more time what independent means?
Independent means one has no effect on the other.
Okay.
Okay, so like, what's the probability? So like, for example, what's the probability that it rains tomorrow, given that if you roll a die, you get a 5?
Disjoint.
What does rolling a die got to do anything with the rain? It's got no effect. They're independent. Right? One has no effect on the other. That's what independent means. And there's a mathematical way of having independence, and there's just a conceptual way of having independence. So here's a frequency table for boys. Girls get crowns, boys get horses. Life ain't fair. Okay, just the way it is. So there's 100 boys. Some of them are princes, some of them are regular boys, some have horses, some don't have horses. And these are the actual values. Notice it's still 60, 40, 10, 90, just like it was with the girls.
Mm-hmm.
The question is, are these independent? Okay, is having a horse or not a horse, not having a horse, independent of being a prince or a regular boy?
independent.
It is independent.
Well, what do you say? I'm sorry?
Independent.
You think it's independent? Well, let's see. What is 10 times 6?
600.
600. Now, these are not percentages, right?
Uh-huh.
So let's convert it to a percent. 8 out of 100 is 0.08. Correct?
Mm-hmm.
10 out of 100 is 0.10. 60 out of 100 is 0.6 or 60. So I ask again, based upon what we just learned a few minutes ago, are these independent?
Dependent.
They're dependent because this number times this number is not that number. Right? If they were independent, then this number would have to be this times this. And this would have to be this times this. And this would have to be this times this. And this would have to be this times this. Once one of them is not, you're done. You don't got to keep checking. It's automatically not independent.
Okay.
Okay, so no, not independent. Not independent. So then it says in the next slide, change the table so that each cell contains the proportion of all boys who fall into that cell. So it looks like it, I don't know. I can't scroll down and keep the screen share going. I'm sorry about that, but it says here, change the table so that each cell contains a proportion of boys who fall into that cell. So let's do that. How do I, okay, annotate. What proportion of boys fall in this cell?
8 out of 100.
8 out of 100, which is 8%. And how many fall in this cell?
0.02.
0.02, 2%, for a total of 10%. And how many are here? What percent's here?
0.52.
0.52, and for a total of 60%, which makes this 40%, which makes this 38%, which makes this 90%, and this has to add to 100%. So we just change it so that each cell contains a proportion of all boys. And you can see from this that they are not independent, correct? So if I clear this and then, no, that didn't work.
Wait, I'm so confused. So we're just putting them all into decimals, but if we do that, didn't we just say that 0.10 times 0.60 is not?
Yes. So, I mean, you can't argue with the data. The question is whether or not it's independent. Because this is not 0.10 times 0.6, it's a different number. They're not independent.
Okay.
Okay. The data you can't change the data. The data is the data. The question is, what can I conclude from the data? So they don't have the values that I want them to have for it to be independent. Therefore, they're not independent. And I don't know why this isn't working. Normally it does, but okay, let's go to the next one. It says, suppose that you had just the marginal proportions as below. Can you use the method that you use for the girls' table to fill in the correct proportion for each cell? And the question is no, you cannot. Because you don't have independence. If you had independence, then sure, 6 and 54 and 38 and 4 and so on. But I don't have independence here. So there's nothing I can do to fill them out. The only way that you can go from having these numbers to having the inside numbers is if they are independent. If not, you can't do anything. So the answer here is no. You cannot. There is nothing you can do. How are you going to get 8 or 8% from these numbers? It makes no sense. Does that make sense, everyone?
Mm-hmm.
Yeah.
So, so here we are. Look at the next slide. Isn't that wonderful? It says, this is the multiplication rule for independent events. If A and B are independent events, then the probability of A and B equals the probability of A times the probability of B. Now, your question from before still remains. Why is this formula true? We're not answering that. We're not answering that. This is just fact. And unfortunately, the answer to it is just a little bit too complicated for this level. If you really want to know, I'll be more than happy to stay after and explain, but it's a little complicated. But if you trust this formula for when A and B are independent, this tells you why this times this gives you the inside square. Okay? So suppose you pick a girl at random from those in the table. Use the marginal proportions and the multiplication rule for independent events to compute these probabilities. What is the probability of a regular girl not wearing a crown? So if I go up to regular girl, that's 90%, correct?
Mm-hmm.
Not wearing a crown is 40%, 0.90 and 0.40. So because they're independent, what is the probability of a regular girl not wearing a crown?
0.36.
0.36, you just multiply. And how about a princess and not wearing a crown? Well, let's go back up. Princess is what probability?
0.10.
0.10, not wearing a crown is what probability?
0.4.
0.4. So what is the probability of a princess not wearing a crown?
4%.
4%, again, assuming independence. Does that make sense?
Yes.
That's just,
I'm confused.
yeah, about what?
How did for the princess not wearing a crown, you got what percent?
1 second. Is there like a radio on behind you or something, a TV?
Yeah, hang on 1 second.
Okay.
So I think what they're asking is that if you can write down the answer right while writing the formula, so we can
Sure.
visually see it.
So
Okay,
here,
my question was, how did you get the answer for P of princess and not wearing a crown?
right here. Princess is 10%, not
Mhm.
crown is 40%. Multiply them, 4%.
Okay.
Because the probability of this
Okay.
and
It's in
this
our chart too.
is the probability of
Okay.
this times the probability of that.
Okay, I get that now.
Okay?
Okay, thank you.
All right. So now we go to slide number 5. So slide number 5 says area models. So area models are often used to help elementary and middle school students, and even beyond that, visualize the multiplication rule for independent events. So let's see how. Example, 3 out of 5 people sing in the shower. You want to find the probability that both your favorite actor and the seasome president sing in the shower. So the first question you have to ask yourself is, would your favorite actor singing or not singing and the seasome president singing or not singing be independent events? Would one affect the other? This is not a math question. This is a common sense question. Would the seasome president singing or not singing have any effect in your favorite actor singing or not singing?
No.
No, they got nothing to do with it unless they happen to be the same person or related or living in the same house or something, which I don't think they are, then they are independent events, which means that we can use what we just learned. If I call A, your favorite actor singing in the shower, and B, the seasome president singing in the shower, then what we're looking for is the probability that both sing in the shower, that A and B. Well, because they're independent, this is just the probability of A times the probability of B. Now, what is the probability that your favorite actor sings in the shower?
How do we know that?
3/5.
3/5, because 3 out of 5 people sing in the shower. So since your favorite actor is just a regular person, if 3 out of 5 people sing in the shower, then it's a 3/5 chance that he sings or she sings in the shower. And what's the likelihood that the seasome president sings in the shower?
3/5.
3/5. Each person is 3 out of 5. So what's the likelihood that they both sing in the shower?
25.
How much? I just couldn't hear.
6 out of 25. No, 9 out of 25.
9 out of 25. You guys see where these numbers are coming from?
Yeah.
Yeah.
3 out of 5 people sing in the shower. So the likelihood that someone sings in the shower is 3 out of 5, assuming that's true. I personally don't. I just kind of crawl into a fetal position and cry. But, you know, everyone is different. So 3 out of 5 people sing in the shower. And therefore, the probability of both, assuming that they're independent, is 9 out of 25. And what we're going to do in the next slide, because I can't scroll down without.
Did you want us to put that into decimal, or can we just leave it like that? Or?
That's fine. It's fine. And what we're going to do is we're going to see this in action in the following area diagram. Because if you look at the area diagram, then what you see is your favorite actor, because it's 3 out of 5, we're going to have 3 sings and 2 does not sing, for a total of 3 out of these 5 be singing. And for the CSUN president, also 3 out of the 5 are singing. How many of these 25 boxes correspond to both of them singing? 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 out of the 25 correspond to both singing, which is why the answer was, as we saw on the previous page, 9 out of 25. The area model was nothing more than a visualization of the formula. So it's not something new, it's the same thing, just shown in a different way.
So is that all we do is just put check marks and that's the area model?
Well, basically, check marks, shading, X's, it doesn't make a difference what you do as long as you're saying these boxes are what I want and this is the total number of boxes.
Okay.
Okay. We're going to skip this one because it just takes too long and doesn't really exhibit anything new, but we'll do this one instead because it's shorter and easier. So it says, example. You spin the spinner twice. What is the probability that it lands on yellow both times? What's the probability that it lands on yellow both times? So first, ask yourself, are the 2 spins independent or does one affect the other?
Independent.
They're independent.
They're independent, okay? Because you can't use the formula that this chapter is all about unless you know that they're independent. You can't just say, oh, we're in chapter 6, that's independent, so they're independent. No, ask yourself, are they independent? Now, of course, I don't mean that you spin it once and then you give it a slight nudge because you like where it ended, right? That's how we cheat, right? You know, it's kind of like rolling dice by putting them down. We're assuming a legitimate spin. So the probability that's yellow twice, the probability that it's yellow and yellow is then equal to the probability the first one is yellow. We'll say y equals 1. The first one is yellow times the probability that the second one is yellow. Now, what is the probability that the first one is yellow?
1 out of 4.
1 out of 4.
Well, it's not 1 out of 4. You're probably saying that because you see 4 possible landing zones, correct?
1/6.
But are those 4 landing zones all equally likely? And the answer is no. Blue is 3 times as big as the rest, right? So you have to imagine that you're really subdividing blue into 3 parts, so that's 1 out of 6, correct?
Mm-hmm.
And how about the second spin? What's the probability that it's yellow?
1 out of 6.
1 out of 6.
And therefore, what's the probability that they're both yellow?
1 out of 12.
What?
1 out of 36.
1 out of 36.
1 out of 36. 12. What the hell? 1 out of 36.
And that's what my brain did first.
I understand. I understand.
I'm sorry, what page slide are we on right now?
10.
I'd have to turn it off to see, but I'll turn it off.
10.
10.
Okay, thank you.
10. It's the one with the spinner. Now, what is the probability that it lands on red the first time and on blue the second time? And Megan, I'm going to give you the chance to get this one. Red the first time and blue the second is going to be what?
Okay, blue the second would be 3 out of 6. And then red the first time is 1 out of 6.
For a total of?
3 out of 36, which would be 1 out of 12.
So we're going to say that your answer to the last question, you were just so advanced that you were actually answering this one. We're going to go with that.
Sure, why not?
Does everyone understand why this is correct for this case? Again, it's 2 spins and they're independent. So red the first time is 1 out of 6 and blue the second. Well, blue is actually 3 times as likely. So if I split it up this way, you can see it's 3 out of 6, 3 out of 36 becomes 1 out of 12. Oops. Okay. Here's another one on slide 11. You flip a coin and then roll a die. You flip a coin and then roll a die. Megan, help me out here. You flip a coin and then you roll a die. What is the probability that you get a head and then a 6?
Is this a non-dependent?
Well, when you flip a coin and you flip a die, does one affect the other?
No,
So are they independent or not independent?
they're non-independent.
They're independent.
You mean they are independent?
They are independent. Okay.
So what is the probability of getting a head?
1 out of 2.
1 out of 2. And then if you roll a die, getting a 6
1 out of 6.
1 out of 6.
for a total of what?
1 over 12.
1 out of 12. Amazing. You're so advanced that you were answering both of the next 2 questions. That's crazy talk.
So me.
Now, of course, the rule can be extended to not just 2 events. It could be even 3 or 4 or 10 or a million, as long as they are independent. So you flip a coin, you roll a die, and then you roll 2 dice. Do any of those 3 have any effect on any others of those 3?
No.
No, they are independent events. They got nothing to do with each other, correct?
I'm
So-
having confusion on like figuring out independent versus dependent, because I would have answered that yes, because you're rolling a second die. Wouldn't that second die have something
No,
to
no,
do
no,
with
no,
the
no,
first
no.
die?
You're not rolling a second die. You're rolling 2 dice after you rolled the first die. So imagine there's 3 tables. The first table has a coin, the second table has a die, the third table has 2 dice. You flip this, you roll those. Right? Those 3
Okay.
things are 3 different tables, right?
Right.
So does the rolling 2 dice over there affect the rolling of a die over here?
No, but can you give me an example of what would be
What would be
like
dependent?
again? Yeah.
Sure. So suppose you have jelly beans in a bag of all different colors.
Okay.
Now, we all know that purple is really the best jelly bean to have, because anyone who says otherwise just doesn't know what they're talking about, right? Purple is the best by far. Now, if you roll into a bag, if you reach your hand to the bag, and I say, what is the probability of pulling out a purple jelly bean? It'll be some number depending on how many purples there are and how many jelly beans there are, correct?
Correct.
Okay, now, you eat that jelly bean because it's really good. And then you reach into the bag again and you pull out another jelly bean. And I say, what's the probability of the second one being purple? Well, there's a different number of jelly beans in the bag now than there were before. Right?
Oh, okay. So then your answer would be dependent on.
Your answer to the second depends on what happened on the first.
Okay. That makes more sense now.
But in this case, it doesn't, right? In this case, what happened in this table and this table and this table are independent. They got nothing to do with each other. Now, I'm really craving purple jelly beans right now. So we might have to end class early for me to get, no, okay, I can hold off. Okay, so let's go. So you flip a coin. What's the probability to get a head?
1 out of 2.
1 out of 2. Then you roll a die. Getting a 6 is what?
1 out of 6.
1 out of 6. Then you roll 2 dice and you want a sum of a 5. What is it?
2 over 6.
No, it's out of 36. I need the chart.
It is out of 36. There's 2 dice now. How much?
4 out of 36.
4 out of 36.
There we go.
And then I would simplify. 4 over 2 is 2. 2 over 6 is 1 over 3. And then I get 1 over 108. So there's less than a 1% chance of this happening.
Can you show that math again when you're canceling out?
What's 4 over 2?
2,
That's where this came from. What's 2 over 6?
3.
Well, 3 in the bottom.
Oh,
That's where this came from. And then 3 times 36 is just 108.
oh, thank you.
No problem. Does that make sense so far?
Mm-hmm.
How do I stop sharing? only because it's making me do this. Okay, next slide. We are now on slide 12. More examples. It says, you flip a coin 4 times. What is the probability that they are all heads? So first, ask yourself, flip 1, flip 2, flip 3, flip 4. Are they independent?
Yes.
Yes. They got nothing to do with each other, right? There are 4 independent flips. So if I get all the heads, the first flip, probability of heads is what?
1/2.
2.
Second flip.
1 out of 2.
1/2.
Third flip.
1 out of 2.
1/2.
Fourth flip. Fourth flip. Uh-oh. Huh?
1/2.
And therefore, what is the probability that they are all heads?
1/16.
1 out of 16. Next one's a little tougher. 57% of California students speak English at home. If you select 5 Californian students independently at random. So here we don't have to ask, are they independent? Here they're telling me they're independent. What is the probability that they all speak English at home? So we have 5 events. The first student that I pick, what is the probability that they speak English at home?
0.57.
0.57. I originally wrote these as fractions, but we'll keep it as a decimal. Second student that I pick, what is the probability that they speak English at home?
0.57.
Third student that I pick, what's the probability?
0.57.
Fourth student.
0.57.
Fifth student.
0.57.
And then I multiply these all together and I get whatever I get. And I have no idea what I get. I really don't care. It's just a number. I mean, it's the strategy that matters. Understanding how to solve the problem is really that matters, huh?
It's 0.060.
0.060. So about 6%.
Yeah.
Okay, now a little tougher. What is the probability none of them speak English at home?
Is that
So 0.43 to the 5th.
Awesome.
Yeah.
Yes. 0.43 to the 5th, because again, there are 5 independent events.
Mm-hmm.
The first one not speaking English is 43%. Second one, 43%. Third one, 43%, 43%, 43%. So what is 0.43 to the 5th power?
0.0147.
0.01, we'll say 0.15.
Okay.
So there's a 1.5% chance none of them speak English at home, and a 6% chance all of them speak English at home. Now, I'm not asking for what about if 3 of them speak English at home or 4 of them. That is a more complicated question. We will get to that later. So for now, we're just answering none or all, which we can do relatively straightforwardly. Are there any questions on this?
Mm-mm.
Lots of examples of the same idea. Let's skip the next slide. It doesn't really add anything to the discussion in the interest of time. So let's go to slide number 14. You asked, I answer. What if events are not independent? So it says, without looking, you pick a ball from a box that contains 5 red balls, 3 yellow balls, and 2 blue balls. You then pick a second ball. What is the probability that both balls are red if you replace the first ball before drawing the second? Now, this is key. Tell me in words what this is telling you about this problem. So, Lair?
So it's telling you it's independent.
Awesome. It's telling you that they're independent. Because if you replace the first one, when you do your second pick, you're back to square one, right? It makes absolutely no difference what your first pick was. It's the same exact situation. Do we agree?
Mm-hmm.
So we want the probability that both balls are red. So we're going to have 2 picks. Each one's going to be a fraction. What is the probability the first one is red?
1/5.
Where do you go?
5 out of 10.
5 out of 10.
5 out of 10.
5 out of 10. There's 10 altogether, and 5 of them are red. Correct?
Mhm.
1, 2, 3, 4, 5. And how about the second one?
5 out of 10.
5 out of 10.
Also 5 out of 10. Of course, these are both 1/2. 1/2 times 1/2 is 1/4. Now, suppose you do not replace the first ball before drawing the second. Are the events first ball is red and second ball is red independent now?
No.
And the
No.
answer is no, they are not. But again, I could still answer the question, what is the probability that both balls are red? Let's do the first pick. What is the probability the first one is red?
5 out of 10.
5 out of 10.
5 out of 10. Now remember, you're not replacing it. So what is the probability that the second one is red?
4.
4 out of 9.
Oh, because you took one away,
Took
right?
one away. And not
One
only
is-
did you take one away, you took one red one away. Right? So there's 4 red left and there's 9 altogether left. 5
Okay.
out of 10 is 1/2. 4 over 2 is 2. So the answer now is 2 over 9.
Professor, what if like the first ball you like pull is like not red?
Well, remember, we're only considering the chances that it happens, right? So if it's not red, it's one of the other 5, and I really don't care what's happening with that.
Okay.
I'm just looking for my situation occurring.
Okay.
So you see that it's actually, if you do not replace the ball, it's a little less likely to get 2 reds because you're missing a red, right? So the second one's a little bit harder to get a red than it was before, which is why the probability goes down. But this is an example of not independent. Does that make sense?
Mhm.
Okay. So this is good. I see this formula now, which means I can answer your question from before, hopefully. Use the following rule when events are not independent, such as when you are sampling without replacement. The example that we just did, sampling without replacement, is a situation of not independent events. So we have the general multiplication rule. It says as follows: for all events A and B, independent or not, the probability of A and B is equal to the probability of the first event occurring times the probability that the second event occurs given the first event has occurred. We just used this formula in the previous example. We had 5 out of 10 for the first event being red, the first ball being red, right?
Mhm.
And then given that the first ball was red, we ended up having 4 out of 9 for the second one. We were taking into account the given of the first to compute the second. Let's do it here again. You draw 2 cards from a deck. One is the probability that the first one is an ace and the second one is a jack. Now, first, if you replace the first card before drawing the second, if you do that, what are we claiming about this situation?
It's independent.
Independent, right? That's translation for independent. You're replacing it, so you're back to where you began. So what is the probability that the first one is an ace?
4 out of
4 out of 52, right? And how about the second one is a jack?
also 4 out of 52.
Also 4 out of 52, and you get, it looks like 1 over 169, which is a very small likelihood. Now, what if you do not replace the first card before drawing the second? That tells you what?
You are now choosing
Independent.
Right? These are dependent, and you got to take into account the first one when calculating the second, right? So the first one is an ace. What's the likelihood of that?
4 out of 52.
4 out of 52. Now remember, you just picked that ace and it is now gone. So what's the likelihood of getting the jack now?
4 out
4
of
out of
51.
51.
Excellent. 4 out of the other 51. And then you get whatever you get. 13. I can't even compute that in my head. I don't want to. Right? I have no idea what that is. So 13. 4
I
out
can
of
keep the decimal.
Okay, what decimal is it?
0.006.
0.006. So that's less than 1%. It's 0.6%. Very small. Does that make sense though so far?
Mm-hmm.
Okay, so let's see what else we got. And we're done with the lesson. Now we have the homework. So we don't have to go any further today. This was a pretty small, and we only did this in 45 minutes because we began at 7:15, which is kind of nice. So
Wait,
let's,
Professor, I
yes,
have a question. Can
Yeah.
you put what was the probability for that last one that you said was dependent? If you don't replace the first card before drawing the second,
you mean what was the formula for it, or what was the final answer?
what was the final answer?
I think it was what, 0.006, was it?
Yeah.
0.006.
And then what were the two fractions?
4 out of 52 and 4 out of 51.
Oh, okay, perfect.
Because remember, because you're not putting it back, there's only 51 cards now.
Yeah. Okay. Thank
Okay.
you.
In a way, it's kind of like our quiz last time with the two passenger cars, because after you pick the first car, there's only 7 left for the next one, right? It goes down by 1. So there's they're all connected. So do we talk about the test? No, we're going to do that now. We finished chapter 6 today. Okay. So the test is going to be this coming weekend because I can't push it off any longer. We're already behind. So here's what I'm going to do. I'm going to put up the solutions. I'm going to write this down so I don't forget. I'm going to put up the solutions to 5 and 6 today. I'm going to put up the quiz for 4 today, which you can do, to be honest, you can do, I don't care. Just get it done this week. It doesn't have to be by Wednesday. If you want to get it done over the weekend, that's fine.
Thank you.
Okay, so get the quiz 4 I'm going to put up today. And then quiz on the test on 1 to 6, I'm going to put up on Friday. And you will have till Monday class time to do it. Okay, so you will have, and this is all the 3 things I got to put up. So you will have, it'll be up from Friday to Monday. And the quiz also will be till Monday. So, just get it done whenever you want. I don't really care. Yeah, and it'll be 1 to 6. What I'll
Is
do,
the test going to be kind of like is it going to be kind of like the quiz that we just had? Can we be able to print out the sheet, do it on there, and then are we sending a picture to your email, or how is the test going to look like?
yeah, that's the easiest way. I think I'm going to require it to be to my @csun.edu email, just because it is by far the easiest for me to grade. So yeah, we'll do it that way.
Do you want just the answers or the work too?
Always show the work. Always show the work, because an answer with no work, I have to wonder how you got it. So always show the work.
Okay.
Whatever you're like. Now, if you can do it in your head and there's no work to show, you can explain your logic sometimes, like this is how I got it. But there should be some kind of justification for every problem. Okay. Even like even a diagram like dot, line, 5, 3, 1, 2, whatever the numbers are, just so I have an idea of where it came from.
How many questions will the exam be?
Somewhere between 1 and 1,000,000, I would say. Probably closer to 1, but maybe like around 10.
Okay.
Somewhere in that vicinity. I haven't written it yet. So
on Wednesday's class, would there be, I mean, I know it's chapter 1 through 6, but there was a lot in this chapter. So is there specific, like, because I know you said that we wouldn't really do like a